Okay, so today we're going to go through derivatives. So you should all be familiar with derivatives from high school, but we're going to start from the beginning, as always. So the definition for the derivative. Okay. Okay, please just keep the noise down while I'm trying to teach. Okay, you might think you're having a small conversation on the side, but trust me, I can hear you. Okay, so definition of the derivative. There's a few notations for the derivative. I'm sure you're aware. We'll mix and match as we go through. So you might have seen it as df by dx, or you might have seen it as f prime. Either way, we'll use both as we go through the examples. Okay, this is defined as the limit as h goes to 0 of f of x plus h minus f of x over h. Okay, so we know what a limit is. We define the derivative in terms of this limit. Now, when we say h goes to 0, we know what that means. H goes to 0 plus, we need to check, and h goes to 0 minus, we need to check. Now, as we go through, I'm not going to keep reminding you of that, but whenever you see limit, x goes to a, you always need to check a minus, a plus. Okay, so I'll remind you as we go through, but later on, I will stop reminding you of that. Okay, so we say that a function f is differentiable at x equals a if this limit exists. So if the limit as h goes to 0 of f of a plus h minus f at a over h exists. Yeah. So here we have the definition for differentiability. So given some function f, I can ask you, is the function continuous at a? You know what that means? I can then ask you, is the function differentiable at a? Okay, and you can follow on with this. Okay, so please make a note the definition for differentiability. Okay, now instead of doing things from first principles all the time, so like you did in high school, so given a function, you would substitute it, evaluate the limit, you'd get your answer. Okay, now we're not going to do from first principles for everything. Okay, that's too long. Instead, we're going to use the rules for derivatives. Now, these rules can be derived from the definition, and we'll do that. But please, test, exam, so on, don't do it from first principles, rather use the rules. Okay, much quicker, much easier. Okay, so rules for derivatives. Okay, so rule number 1, if we have the derivative of some constant c, then this is going to be 0. Okay, some of these I'll prove for you. So how do we get this? I'll prove a few of them for you. The rest I'll leave for homework. Okay, so rule number 2, the derivative of x to the n is n x to the n minus 1. So if we have x squared, for example, we take the 2 down and then minus 1 from the exponent. So then it will be 2x. If we had 3x cubed, we would take the 3 down, then it would be 9x squared. Okay, so we call this the power rule. Right, because it's x to some power. Number 3, we have the derivative of some constant times a function f. So if we have a constant times the function, this constant we can take out of the derivative. So this will be c times, and then the derivative of just the function. Okay, so constants we can take out of the derivative, they do not affect it. Okay, number 4, if we have the derivative of f of x plus or minus g of x. Okay, plus or minus, it doesn't matter. Then we can take the derivative of each one separately. So this is going to be df by dx plus minus dg by dx. So here the derivative was outside the sum, and now we have the sum of the derivatives. So it distributes onto each function. Okay, number 5. We're going to be using this quite a lot. The derivative of a product of two functions. So f of x times g of x. Okay, we call this the product rule because it's a product. This is given by df by dx times g. So we take the derivative of the first function, we leave the second function alone, plus, now we leave the first function alone and take the derivative of the second. Okay, we call this the product rule. Right, because it's a product rule. Okay, number 6. Okay, similar to number 5, but instead of a product, we have a quotient. So it's going to be d by dx of f of x over g of x. Okay, and again, we can write this similar to number 5, but it's going to be df by dx times g of x. Okay, but now a minus. So for the product rule, comes with the plus between the terms. This rule comes with the minus between the terms. Okay, and all of this is divided by that denominator squared. Okay, we call this the quotient rule because it's a quotient. Okay, and lastly, rule number 7. We have d by dx of f of g of x. So here we have a composition of functions. We know what that is. So f on the outside, g on the inside. This is going to be f prime of g of x. So we take the derivative of the outside function. We leave the inside bit alone, multiplied by the derivative of the inside function. Okay, we call this the chain rule. Okay, it's a bit of an odd name for now, but later on when we get to more complicated functions, we will see that f of g of h, we end up with a chain of derivatives. So we have the outside derivative, the inside derivative, and then the innermost derivative. So it's a product of all of them. We call it a chain of derivatives. Okay, hence chain rule. Okay, but we'll see that later on. Okay, just this one, f of g, that's all you need to know for now. Okay, so these rules here can all be derived from first principles. So if I give you, for example, this rule number 3, a constant times a function, what you can do is take this constant times a function, substitute it into the definition, and you'll see simplify, you end up with the right-hand side. Or if you take number 2, if you take the function to be x to the n, you substitute it into the definition, simplify, and you end up with the right-hand side. So all of these rules come straight from the definition. Okay. So we'll prove some of them in class. The rest of them I'll leave for homework. But all of them are exactly the same. Take the function, whatever this is, substitute it into the definition, simplify, and you get this right-hand side. Okay, so all of them will be like that. Except number 7, a bit more complicated, but we'll go through it. Okay, so rules, let's sit 4, that's pretty easy. I'll leave that for you to do. 1, okay, you don't need to prove that. That's quite obvious. 2 we'll do. So let's have a look at 2. Okay, yeah, so number 1, pretty obvious. I'm not going to ask you anything on that, right? If it's a constant, of course, the derivative is 0. You don't need to prove that. Okay, but number 2, let's have a look at that one. So we want to show that the derivative of x to the n is n x to the n minus 1. Okay, so whenever you're proving something, go from the definition. So that left-hand side, the derivative of x to the n, that is secretly that limit. So we're going to write that as the limit. So this is going to be d by dx, x to the n. That is going to be the limit as h goes to 0 of the function evaluated at x plus h. So it's going to be x plus h to the n. Right, because that's the function. The function is x to the n. If I substitute x plus h, I get x plus h to the n. Minus the original function, so minus x to the n, and then all over h. So all I did was take my function, x to the n, substitute it into the definition, and I get that limit on the right. Now what we want to do is simplify that limit until we get to this point here, n x to the n minus 1. That's the goal. Okay, so when proving this, you know what you should be getting to. Okay, that's already given. The only thing to fill in is the steps in between. Okay, so we've got our starting point, we've got our ending point. Let's see what we can do. So this will be the limit as h goes to 0. Now we have x plus h to the n. There's only one thing we can do with that, expand it out. Right? If it was x plus h squared, you would expand it as a square. If it was x plus h cubed, you expand it as a cube, a plus b cubed. So we do exactly the same thing. But when you're expanding something to the power n and you don't know what it is, we need to use, what do we use? Think back to the first week. Binomial. So this is going to be the sum, k equals 0 to n choose k. We're going to have x to the n minus k and h to the k. Okay, if you don't know that, go back to the notes from week 1 and review your work. Minus x to the n, and all of this is still over h. Okay, so that first term, x plus h to the n, I expanded using the binomial theorem. Right, that was all the way back here in lecture 1. There we go, binomial expansion, lecture 1. We did all of that. Okay, so please go back to lecture 1 if you still need to go over that. Okay, so now we've got this sum over here, minus x to the n. We want to try to simplify this a bit. So let's write out a few terms from the sum just to see what it looks like. So this is going to be the limit as h goes to 0. Now for the sum, I'm going to write out a few terms. So when k equals 0, we have n choose k. Okay, that's going to be 1. K is 0, so we end up with x to the n. And again, k is 0, so h to the 0, that's just 1. So the first term, that will be x to the n. Okay, plus, and now let's look at the next term, k equals 1. So we have n choose 1, so that's going to be n. Again, k is 1, so it will be x to the n minus 1. And again, k is 1, so we have h. Plus, and there's some other terms there, so let's write out the next one. It will be n choose 2, so n minus 1 over 2, x to the n minus 2, h squared, and the pattern continues with that. Okay, plus dot dot dot, okay, for however many terms there are. And then right at the end, we have minus x to the n. All over h. Okay, don't forget we're still dividing by h. Now, some things will cancel. X to the n right in front, x to the n right at the end comes with the minus, so they cancel. Next, all of those terms in the middle have a h. We've got h, h squared, h cubed, h to the 4. They all have some h in common. And we have h at the bottom. So we can cancel them. So this one cancels with this one. One of these will cancel, so that will go down to h. H cubed will go down to h squared, and so on. So now this will be n x to the n minus 1. Then we have plus the limit as h goes to 0 of all of those terms that still have h in them. So it will be n minus 1 over 2, x to the n minus 2h, plus dot, 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 and all of them have h, some power of h. Now, what are we doing? We're taking the limit as h goes to 0. The first term is h, so that will be 0. The second term has h squared, that will also be 0. The third term will have h cubed, that will go to 0. All of them go to 0. So this one goes to 0 because there's the h. The next one goes to 0 because there's h squared. Next one goes to 0 because there's h cubed, and so on. All of them go to 0. So all we're left with is that very first term that never had h, and that was nx to the n minus 1, which is what we wanted. Yeah, and that's the end of the proof for that one. Okay, so all of the proofs follow in a very similar way. You take whatever the function is, you substitute it into the limit definition, simplify however you need, take the limit, and you get your answer. Okay, so that was number 2. Number 3, I'll leave that for you to do. Number 4, you can do that as well. Let's have a look at number 5. So number 5, that was the product rule. So what we want to show is that the derivative of a product can be written as the derivative of the first one, leave the second one alone. So it will be df by dxg, plus then we leave the first one alone and take the derivative of the second. Yeah, so that's the goal. We want to start off with this left-hand side here, and on the right we want 2 terms. The first term must have the derivative of f, the second term must have the derivative of g. Okay, so let's start off with the definition and see where we go. So the derivative of the product is equal to the limit as h goes to 0. We want whatever this is evaluated at x plus h. So that will be f x plus h, g x plus h. So for the first term, it's always whatever you got there at x plus h minus the original. So minus f of x, g of x, all over h. Okay, so that's our starting point. What we want is to write this limit as the sum of 2 terms again, where the first one comes with the derivative of f, and the second one comes with the derivative of g. So just on the side here, let's write out what those will be. So this, the derivative of f, that's going to come with some limit definition. So that will be the limit h goes to 0, f of x plus h minus f of x over h. Okay, but over there we don't have that. Okay, we've got a product of f and g and then another product of f and g. What we want to do is try and separate them into one part with f and another part with g. And then over here we have limit h goes to 0, g of x plus h minus g of x over h. Okay, so again, that's what we want. We want the first limit, top right there, being multiplied by g, and we want the second limit, top right there, multiplied by f. Currently, we don't have that. So what is missing from what we have here, from here, what is missing from there to end up with those 2 limits at the top? There's something missing. So we're going to add that. So this is going to be equal to the limit as h goes to 0. We'll keep all of that, and then we'll add in what's missing. So that will be f of x plus h, g of x plus h, minus f of x, g of x. Okay, let's add in what's missing. What's missing, if we look back here, are these terms. If I multiply that limit by g, I'm going to end up with f of x plus h, g of x, if you look at the product there. So f of x plus h, g of x, that's missing from that first term. Does everyone see that? Take the limit, f of x plus h minus f of x over h, and multiply it by g, this here. Okay, so take the limit, multiply by g, what do we get? We get f of x plus h times g minus f of x times g. Everyone see that? Over here, I have f of x times g. I have that. But I do not have f of x plus h times g. I have f of x plus h times g of x plus h. This is missing, that product. Same thing with this other side. Notice with the multiplication, I have f of x times g of x plus h. Everyone see that? Okay, f of x times g of x plus h in the limit there. But over here, I don't have that. It's missing. So what I want to do is add in those missing terms so that I get the limits on the left there and then the limits on the right. Okay, so let's add in what's missing. Well, we know what's missing. It was that f of x plus h times g of x. So let's add that. Okay, that was missing from that green part in the top right. But I can't just add something. Okay, you're just changing what it is now. So if I add in that term, I then need to subtract that term as well. Right, you can't just add something just because you need it. You're changing stuff. So if I add the term, I need to then subtract it. This is all still over h. Okay, so everyone see what I did there? Okay, so f of x plus h times g of x, that was missing from this first limit. This one over here, this limit there. If I multiply it by g, like I have on the right there, this first term will be f of x plus h times g. That's missing. I don't have that. So I add it, but that's changing the expression now. I can't just add something for nothing. I need to subtract it again. Okay. So what does this accomplish now? We end up now with 1, 2, 3, 4 terms. Does everyone see that? 1, 2, 3, 4. 2 of them are going to end up being this first limit with the g. The other 2 are going to end up being the second limit. They're the one with the f. Okay, so what we want to do is collect the terms so that we end up with the first limit and the second limit. Okay, so what do we need for the first limit? For the first limit over here, this one here, f of x plus h minus f of x. Everyone see that? Yes, no? I'm pointing. Can you see the arrow? So you can see. Okay, yeah, there. F of x plus h minus f of x. I want that to be my first limit. And I'm multiplying it by g. Okay. So let's just make a little note here. So all of this times g. That's this in pink. Everyone see that? Okay. Then in blue, this part will be this times f. Okay. Everyone see that? Okay. So what we want to do is look at this. We've got some number of terms. We want to rewrite it so that the first 2 terms give us this part in pink. And the second 2 terms, doing some reorganization, gives us this part in blue. Okay, so what are we going to do? We're going to write this as Okay, so this is going to be the limits as h goes to 0. Now I'm just going to reorganize the terms a bit. So I'm going to write this as f of x plus h, okay, into g of x plus h minus g of x. So the terms with f of x plus h are grouped together. Everyone see that? Okay, so there's f of x plus h with g of x plus h, and then the second from the end there, f of x plus h, g of x. I put that together. That last one I put together there. Okay, plus, then I'm going to take out a g of x, and what's left over? So let's look at the terms with g of x that's left over. It's going to be that second to last term, that comes with a g of x. Okay, minus, and then that second term in white there, that also comes with a g of x. Okay, and all of this here is still divided by h. Okay, so I've grouped it into two parts. The first part, the g of x plus h and the g of x are put together. Okay, I hope you can see that's going to end up becoming a derivative. And then right at the end there, I took out a g of x, and I'm left with f of x plus h minus f of x. I hope you can see that's going to become another derivative. Everyone see what I did? Yeah. So let's write this as the limits. H goes to 0, f of x plus h. Then the limit, I'm just using the limit laws. I can split up products like this. Limit h goes to 0, g of x plus h minus g of x over h. So that's stuff in the square brackets. I made its own limits over there. Plus, and then g of x can just be by itself there. And then again, the stuff in the square brackets, I'm going to make its own limit. Yeah, so that will be f of x plus h minus f of x over h. Okay, so we've done what we wanted. We got 4 terms, and we split it up into 2 terms that give us the derivative for g, this part, and then 2 terms there where we have the derivative of f. Because now we can write this as f of x times, this limit is just the derivative of g, plus, and then that limit over there, well, that's just the derivative of f. Okay, times g of x. Okay, and that's what we wanted. Any questions? Okay, again, this is not baby school. I know you have questions, but you're not asking. Are there any questions for this? Okay, big school now, you need to think for yourself. Do you understand it or not? No. Now you need to think a bit more. What part did you not understand? And then we can make some progress. Okay, so someone want to be brave and ask the first question? Yes, thank you. This part. Yeah. So here I'm reorganizing the terms. So let's make it a bit bigger and then I can point at it. Okay, so remember we wanted one of the parts to be derivative of g. We wanted the other part to be derivative of f. So let's have a look at this line here. We got all of this. What we want to do is build up the derivative of g. So what do we need? What is the top part for the derivative of g? Gx plus h minus g of x. Let's look for those terms. Here's g of x plus h. Okay, what else do we need? G. Where's that? Yeah. Yeah. We put that together. Yeah. So this f of x plus h, this one, and that one, we put together into one. So we factor out f of x plus h, that stays here. And what are we left with? G of x plus h minus g. That's what we wanted. So we take this term, we take that term, we put it here. Because we want this. That's done now. Those terms you cross off, we're done. Next, we need the derivative of f. What do we need to make the derivative of f? F of x plus h minus f of x. That's what we want. So let's look at the terms with f of x plus h and f of x. This one, we've used already. It's gone. That last one, we've used already. It's gone. So what do we use? The middle two. There's nothing else we can do. That is it. So we've got these middle two. This comes with the g of x. This comes with the g of x. What do you always do in algebra when two terms have a common factor? You factor it out. This has g of x. This has g of x. We take it out. What's left? F of x plus h minus f of x. What is this? Derivative of f. Yeah. Any other questions? Yes. Doesn't matter which one I have first. Well, here and here. This one. This one. The pink and the blue. Yeah, which one comes first? No, you can swap the order, doesn't it? The pink one with the G. Yes, that's going to be this one. I don't understand what you're saying with the order. So this one. Okay, let's go back a bit. This one. Yes. No, we're multiplying two functions. The order doesn't matter when you multiply. Yeah, you can have this times this or this times this. You're just multiplying. It doesn't matter. Like x times sine of x or sine of x times x. It's the same thing. Yeah, the order doesn't matter. You can swap it around. Okay. Anything else? All good. Okay. Next one. So that was proof 5. 6, that's for homework. You can try that out. Very similar to this one. Yeah, very, very similar to this. So here, we added these terms to get the two limits. We're going to have exactly the same thing, but with the minus. Yeah, it's exactly the same sort of setup. Okay, so that's 6, and then 7, we'll do that now. Okay, just a note, if you don't do the homework, you're going to have a very, very unhappy time during the test and the June test, just by the way. So I strongly suggest you do the homework for this part. Hint, hint. I don't know if I can make the hint any stronger than that for the test and the exam. I'm not telling you what's coming out, but do the homework for this bit. Okay, so proof for number 7. This one's a bit odd, but we'll go through it step by step. So we start off with this f prime. Okay, we're going to write it a little bit differently. Instead of writing the limit h goes to 0, we're going to write it as the limit of delta x going to 0. Okay, instead of h, I'm using delta x, same idea. This is going to be f of x plus delta x minus f of x over delta x. Yeah, it's exactly the same as the h, but later on I need other variables, so I'm going to call it this. Okay, now f of x plus delta x minus f of x, that's a difference in the function f. I'm going to write that as delta f over delta x. Sorry, with the limit. So limits delta x goes to 0, delta f over delta x. Okay, it's just notation. Okay, don't be too stressed about that. So instead of the h going to 0, I'm just calling it delta x at the bottom. And then the difference between the function, I call delta f. Okay, just notation, everything is the same. Okay, now we're going to define something called epsilon. So epsilon is equal to delta f over delta x minus f prime of x. Okay, so I'm going to define this Greek letter epsilon. You know your Greek letters? Okay, learn your Greek letters. Okay, so we've got the Greek letter epsilon. It's like E, but in Greek. So epsilon is this difference here without the limit. Okay, so I'm just taking delta f over delta x minus f prime, no limit. If I were to take the limit, then those two would be equal, and this epsilon would be 0. Does everyone see that? Okay, this, no limit. No limit. Delta f over delta x, no limit there. If I were to take the limit, I would have this. But what is this? This is f prime. What is f prime minus f prime? 0. So if I took the limit, I would get 0. Okay, that's all you need to understand for this. So here, if I take the limit, delta x goes to 0 of epsilon is the limit delta x goes to 0 of all of this. Okay, but the limit of the first term is f prime minus f prime, that's 0. Okay, that's the only thing to keep in mind for now. Okay, we're going to be using that at the end. Okay, so put a little big cloud around here. We're going to use this at the end. Okay. Now, let's go back to this epsilon here. So epsilon is delta f over delta x minus f prime of x. Okay, what I want to do is solve for that delta f. Okay, just that numerator. I want to solve for that. So let's multiply through by the denominator. So I end up with epsilon delta x is equal to delta f minus f prime of x delta x. Okay, again, I want to solve for that delta f. So I'm going to take that second term over to the other side. So I end up with delta f is equal to f prime of x plus, times delta x. Okay, and I took it over to that other side. So we'll end up with the epsilon delta x. Okay, so all of this is just some pre-working stuff. Basically, instead of doing all the algebra stuff later on, we do it now, and then we just substitute. Okay, so this is the second important thing we're going to use. Okay, so important thing number 1 in the cloud, important thing number 2 in the box. Okay, so let's start with the proof. So what we want is to show, that the derivative of f of g of x is f prime of g of x times g prime of x. That's what we want to get to. Now we're going to do a little bit differently. We're not going to use the limit definition. We're going to use something else. But behind the scenes, it's the same thing, right? Because we use it over here. Yeah. So we are using the limit definition, but we're just rewriting it a bit differently to make the proof a bit neater. You can try it the other way. I encourage you to do that, but we're going to try it this way. Okay, so that's what we want to show. Let's have a look at the proof. So suppose g of x is differentiable. We know what that means. It's differentiable at, let's say, a. So at x equals a, g is differentiable. We know what that means. Okay, and f of u is differentiable at g of a. Okay, so I'm using f of u because x is being used already. So we've got this function g of x, it's differentiable at a. In other words, g at a, that limit exists. Next, f of u, okay, f is differentiable at g of a, whatever that point might be. Okay, now for f and g, we're going to use this box equation here. Okay, so we end up with equation 1. Okay, let u equal g of x. Okay, makes things a little bit easier. So we're going to use this box equation. Delta f is f prime at x, delta x plus epsilon delta x. Okay, so delta u, okay, is going to be equal to g